So this is going to be our 10th lecture on power system operation and control. So we have almost, so basically we get around 40 lectures for this course and we have reached 10th. So that means we have almost covered 25%, and the next 25% is going to be very interesting because it will start power system problems and using of all these optimization problems, how to use these optimization methods in solving those power system optimization problems. So probably I'm expecting around 2 more lectures I'll need for basics of optimization. So probably by Wednesday we'll complete the optimization part, and from next Thursday we'll come back to power systems, and then we'll see how power system problems need methods of such type for solving these optimization problems. So okay, anyways, so yeah, let us start our 10th lecture. So we, in the last class, we anyway discussed a nonlinear problem. We discussed about Newton's first order gradient technique, and we saw that handling of inequality is actually a big issue, and this is going to be this is actually an issue in a lot of optimization problems. That's why when you are modeling your optimization problem, because in your second year you will be doing your research. If you are doing a research which involves optimization, so you have to be a bit careful while handling this inequality constraints. And I said that Newton's first order method is also known as a steepest descent technique because it moves towards the steepest descent way. We saw the solution procedure, how this method is solved. I hope this is clear, and we discussed a few advantages and disadvantages of these methods, and eventually we got to know that this works fine for a decent size of problem, but yeah, it takes a bit of more time to convert. So because we are doing it in iterative fashion, it might take more time to convert. So that's why this method is least popular. Now let us start the next method, which is Newton's second order gradient method, and this is the most popular method. And even as I told in the last class, also even the interior point method is based on this method. So this is going to be this actually solves all the KKT conditions simultaneously. So the key here is simultaneous solution. Simultaneous means because in the first order method we were, let's assume x was the dependent variable and u was the control variable. So what we were doing is we were taking derivative separately, x we were taking derivative separately. But here in combination we call them as z, and we take just the derivative of z, so partial derivative of Lagrange function with respect to z. So basically by considering everything simultaneously, it actually solves the purpose, and it fasten the process of convergence. So as I said just now, that z is, they assume z, which is a complete set of variables which include all x and u. All x and u means all dependent and independent variables, and you take you take the first order derivative, which we call it as gd, and we satisfy that equal to 0. So anyways, we want the optimal solution of any optimization problem is going to always be when the derivative, first order derivative, is set to equal to 0, right? So this optimality condition is going to be this gd equal to 0. So basically from the power flow, if you remember how we solve, so if let's say we have a gd specified minus gd calculated with respect to the Hessian matrix. We call this double derivative matrix as a Hessian matrix because in I'm just correlating it from the power flow because that you have already studied. So in power flow we say P specified minus P calculated is equal to the Jacobian and into the delta theta and delta v. So this is the way we write for, and there will be q and v also. Q is specified and q calculated as well. So this is the way we do it for power flow. But what happens here, because this part here, this is anyway of a derivative. This is not here, there is no derivative on the left hand side. So here we anyway have derivative, which is the first order derivative. So then the left hand side, which is this part Jacobian here, or this part here Jacobian, because there is no derivative here, so Jacobian is first order derivative. Because in here we have the first order derivative on the left hand side, so the right hand side will be double order derivative. So that's why we say it is partial double derivative of in terms of z, and then we want to estimate delta z. And this matrix is actually known as Hessian matrix. So whenever you have a double derivative of a function, you call it as a Hessian matrix. When we have single derivative of a function, we call it as a Jacobian matrix. So it's a nomenclature given to naming of this two matrix, which is given and which is followed. Now coming back to this Newton's second order method, we say that this GD specified, we already mentioned here that at the optimality it should be equal to 0. So GD specified is going to be equal to 0, and eventually we want to solve this problem, right? If we solve this problem, which will be nothing but delta z is equal to let's say if I call this a Hessian matrix as H, so it will be H inverse GD calculated minus. So we have to solve this in an iterative fashion, and with this solving we will get the optimal solution. So yeah, so this is this is a very simple way of doing it, and this small change of including all the dependent and independent variable in one set has resolved a lot of issues. So for example, so I hope you got the idea how we actually solve this optimization problem. So once you solve this optimization problem, and then you again go back to the second step, you keep on doing it till your GD calculated is equal to 0. As soon as you arrive at this, you stop the iteration. Right, I hope it is clear to everyone. So this is the way we actually solve the Newton's second order method. Here again, we are adding a penalty, and this logic is same what we have seen in the first order method. You can either enforce a hard penalty or a soft penalty. It's your choice, what we have observed previously. So you can do both way, but again it is logical that we should go for soft penalty. It is my preference. Hard penalty is always difficult to manage, so always prefer soft penalty. And it is I hope it is very clear why we go for soft penalty, because it is kind of a let's if we talk about voltage, so we saw that the voltage will be, or whichever inequality is violating, you will write them in this fashion, or if I write in a generic sense, it will be like hx u minus hx u lower bar if it is hitting the lower limit, or upper bar if it is hitting upper limit. So you can add a penalty here, and it will become much simpler. So this way you actually gradually try to shift the solution to an optimal solution, and you bring the value within the limit. So that is actually very useful. If you enforce a hard penalty, then the flexibility what an optimization problem can get to satisfy or to find out a better solution, that getting might be difficult in some set of problems. So that's why I always prefer a soft penalty, but yeah, you can do depending on your problem what you're solving. So I hope this concept is clear what of Newton's second order gradient method. Now let me just go to the some comments about this method. The most best advantage is it gives you a very powerful convergence, because you can imagine this is very similar to power flow. So the Newton's first order, you can correlate it with respect to the Gauss-Seidel method, and Newton's second order you can correlate from the power systems power Newton-Raphson based power flow method. So you can imagine, because I'm sure you must have studied that in your bachelor's course. So Gauss-Seidel generally takes more number of iteration to converge, and Newton-Raphson converges very fast. So you can imagine, or you can correlate that this from that Newton second order also gives a very powerful convergence. But on the other hand, it has a big disadvantage of handling inequality constraints, because it against not able to handle inequality constraints, because the main reason is you are eventually anyway, to handle this inequality constraints, you are adding a penalty function in the Lagrange function, and adding of this penalty function is uh, either either you go for hard penalty or a soft penalty. It keeps on switching on and off, because in each iteration you have to check whether a penalty has to be added or not. If yes, then you will add it. So probably it keep in a convergence pattern. If you see the objective function value, or the Lagrange function value, if you see in each iteration, as we go on here in iteration, the solution will might give you a jerk that suddenly it will start increasing, because this jerk is coming because of this penalty function, because it might till here there might be no penalty, but suddenly there is some penalty coming up, because of which this jerk is coming up, and because of this jerk it again creates a problem in solution. Right, I hope you agree that how this issue is there. Now, let me tell you about interior point method, which I was telling you before, that it was developed by professor, or a mathematician, Karmarkar. He is an Indian mathematician. He developed a simple concept of adding or handling of this inequality constraints, which resolved all the issues, and he developed in 1984. So you can imagine it is just probably around 30 years back he developed this. Before that, there was no method to solve or take care of this inequality equation, so people used to use that Newton second order method to solve the optimization problem. So you can imagine that how difficult it was to go to do an optimization and to achieve an optimal solution before this method. So, and especially if you can easily correlate it from a practical or realistic problems, the size of the problem, and with that it becomes really difficult. I hope you can imagine that. So this after this, things got changed a lot. Now, what he did, it was a very simple way, simple method. Anyways, nobody thought about it, but it was a very small change which actually resolved all the issues. And this small change was actually it actually or just let me quickly explain you what he does. In general, if you see all the optimization problems, the solution, anyways, this I'm going to explain you in the tutorial in much more detail. I hope you got this idea in the first tutorial. Yeah, I'm sure you must have got the idea that in the linear programming, what Suraj might have told you, that whatever is the linear problem we have, the solution always lies on the corner points. So here what it does, in the interior point method, instead of searching for all the corner points, what he did, the change what he added into the Newton second order method, here the solution can travel from in between to a global optimal solution. So let's say this is a global optimal solution, and the solution is initially here, or the initial guess is somewhere here. So it can travel somewhere from between, and it can reach to a global optimal solution. And it was a very interesting way of handling it, and it takes much less iteration, much less iteration to arrive at a optimal solution. So this Karmakar's approach was later on developed Basically, people thought that Karmarkar was the first person who developed it, but it was observed by another mathematician, Gill. He observed it in 1986, that there was another scientist, Fiacco and McCormick. They have already proposed this logic in 1968. But when they proposed it, the perception was very different, so that's why it did not got any popularity. But Kaumakar's way of presentation was very attractive and very it immediately make sense for everyone, and everyone adopted it. So the method what he did is very interesting, and it got immediate people started immediately adopting that method, and it became really interesting to solve all the problems. It was able to handle the inequality constraints in a perfect manner, and people started exploring it. And obviously, once a method comes in market, people start developing various variants to it. So for example, let's say whichever company developed mobile phones, it's not the only one company who does that, but there are new companies which come in the same business, and they try to propose, or they develop a product which is having the same use case, but with some different perspective. So obviously, in every business you see, every product you see, or every research you see, everywhere people always try to improve upon the existing product or existing method. So here also people started proposing various different methods, or variant of it. A baseline of the problem was always same, but they developed many variants of it. So the okay. Yeah, so this is just by element subtraction, right? So you have these three set of equation. Here you can see that there is no logarithmic term here. Logarithmic term is no more available here, but you can imagine that if you are going to satisfy this as equal to 0, that means your original Lagrange function, there also this part will be taken care, this part will be taken care, and this part will be taken care of original Lagrange function, right? So this is the way the Karmakar suggested for handling this inequality constraint, and it immediately helped the complete problem to remain within this limit. So basically what is happening here, let's say if we take about voltage, right? So let's say voltage is equal to 1.1, and this point is voltage equal to zero point 0.9. So let's say, because voltage has to remain within this limit, right? Now because of this logarithmic barrier, what will happen is it will always ensure that the voltage always lie within this range. It will not allow to go in this direction, because log of the equation is like this. So v should be less than equal to 1.1. So this implies v plus s is equal to 1.1, and this s has to be greater than equal to 0. So this s, because it is from as a logarithmic function, and log of s, because if it goes if it becomes v greater than 1.1, so what will happen, this s has to be negative, and we have ensured that s has to be greater than equal to 0. So it will not allow this logarithmic function to go beyond this region. So it will be adding a penalty here, a huge penalty, because log of negative is not possible. So it will add a huge penalty and would not allow the problem to go in this direction. So therefore the solution always remain within this region. So this is the way they handled the inequality issue in this interior point method. Now the solution is again the same what we saw in the KKT condition, that you have to take the derivative. Here I have just taken the sorry, this is this part. So basically as we just now discussed, that GD calculated is equal to minus of h, which is the double derivative, into delta z. So this is this equation. So this is h, which is double derivative. So wk is the double derivative, and delta G. So I have just separated it based on the to make it very simple. And this is the variables which we want to calculate or estimate. One is delta X, delta lambda, and delta Z. And this delta Z is the Z which we have assumed for mu by S. So you got the idea, right? And this part is the GD calculated. So just you have to take this matrix inversion, and then you will iteratively update it, and then you'll get arrived at a optimal solution. And once you arrive at an optimal solution, we will update it using some scaling factor alpha, and then we'll update it to a new variable, or sorry, new assumption. So whatever, this is the old assumption because you need to take an assumption, and this is the new value. So this old value will get updated to new value, and you will keep on iterating it till you arrive at a optimal solution, or simply till you get this GD calc equal to 0, because as soon as you see this GD calc equal to 0, that means you have arrived at an optimal solution. Right. So I hope this concept is clear to everyone. Interior point method and Newton's second order method. Any query here? So I hope you can imagine how very simply or very creatively they have handled the issue of inequality. And it looks very simple. Adding just a logarithmic function resolves everything, and means you can imagine that nobody has thought about it earlier before that. So at times research is like this. You might feel that, okay, this is a very silly thing to add, but people generally finds it difficult to add these or see these small things which can actually improve a lot. So this is valid everywhere, in research, in your life, in your career, whatever you see, you have to just resolve the small things and take a small steps. Everything will be fine. Okay, so let's come back to the problem. Right, so this was the advantages, and there is no typical disadvantage of this method, and by far till today this is the best method to solve a non-linear problem. So, or a linear also, you can definitely solve linear also. So this is the best method till date to solve non-linear method. So there is no method which has came into existence after that which can solve this type of method. Okay, so now let me just quickly give you one example, and with this I'll end this session, today's lecture, and this will give you this is going to be our second tutorials question which I'm going to give you now. Is this two bus problem? So this is actually a power system problem, but I'm just connecting you with giving you some objective function, some constraints, and then you need to solve this using first order gradient method, using second order gradient method, and using interior point method. So you have to solve this, and this is going to be your second tutorial, which anyways, but probably I'll be there on Wednesday again to give you, or you can, anyway, this video I'll be uploading, so you will get this problem from there. So imagine that there are two buses which you can see here. So these are the two buses, and both the buses are connected with a load PD, and both are connected with a generator which you can see here. And delta 1 and both the buses has V1 delta 1, the second buses have V2 delta 2, where I have assumed that V1 is equal to 1 per unit, V2 is equal to 1 per unit. Delta 1 is 0 because this first bus is a reference bus, so I have assumed that delta 1 is equal to 0. Delta 2 we have to find, PG1 PG2 we have to find. The line admittance is y is equal to 1 minus j10. The load values are all also given here. Now I'm just mentioning that there is some function. It's actually the economic dispatch problem, but I'm not naming it now because I'm going to explain this later on. But just for your understanding, that the objective function is 1 plus PG1 plus 3 PG1 square F2 Pg2 is zero point 0.5 plus zero point 0.5 Pg2 plus zero point 0.5 Pg2 square. See, the objective function is F2 equal to total objective function is F1 Pg1 plus F2 Pg2. So this is the objective function. Right. Now, what will be your equality equations? What will be your gx equations in this? So gx equal to 0. What all equations are going to be there? Can you guess here?
So Pg1 plus Pg2 equal to 4, negating the loss.
Uh, yeah, but actually, because this is, I can understand. Okay, you are thinking from the economic dispatch point of view, but this is actually we have to write a nodal power balance equation. So the at node one, let's assume at node one, the equality equation is going to be like this. So Pg1 minus PD1 should be equal to uh, the equations of Newton-Raphson power flow. That will be V1 V2 Y12 cos theta 12 minus delta 12 plus V1 square Y11 cos theta 11. So this is going to be the first equation. You can do the expansion. Delta 1 theta 12 is the admittance matrix is y, and this is the magnitude, and theta is the angle. So you can write it like this: y angle theta, and voltage, I am mentioning voltage angle delta. So anyway, I have assumed delta 1 as equal to 0, so you just have to take, and v1 v2 both as 1, so you can put all those value here. I'll show it. So let me just write it here. So again, it will be Pg1 minus PD1 equal to V1 V2. We have assumed 1 per unit, so this will go, this will go, this will go. Y12 will be some value you can calculate from here, cos theta 12 minus delta 12 is nothing but delta 1 minus delta 2. So delta 12, you, because I have assumed delta 1 as 0, so this will be 0, so this is going to be minus delta 2. So minus delta 2 means plus delta 2. You can expand this, plus y11 cos theta 11. Right, so this is going to be the first equation, first equality equation. Then there is going to be the second inequality equation, which will be corresponding to node 2. This is going to be Pg2 minus PD2. Again, I missed out in this. PD1 is also 3 per unit, so you can just put the value 3 here, and then you have to find this. And Pg2 minus PD2 will be again the same: V2 V1 Y21 cos theta 21 minus delta 21. So it is 21, right? So delta 21 will be plus delta 2, so it will be delta 2 plus V2 square Y22 cos theta 22. Right, again, if I expand this, because I know some assumptions, so Pg2 minus PD2 is 1 per unit, so it will be minus 1 equal to, we know V2 V1 is 1 per unit, so it will go Y21 cos theta 21 minus delta 2 plus Y22 cos theta 22. Right, for the time being, you can ignore the reactive power type of reactive power constraints. You can assume it is infinite reactive power is there, so you can easily ignore that. So right, so these are the two, G1x and G2x. So let me just write, this is G1, this is G2. Now let us talk about inequality. Inequality, what could be the inequality here? Can you guess? One, you can say that generation upper limit, lower limit. Other, because voltage we have already assumed, so there is no going to be no upper limit, lower limit. So if let's say we ignore, huh?
or angle, a lot angle.
Angle, yes, delta 2 is there, we can actually assume the limits of that. So for the timing, let's ignore all the inequality constraints, just assume this equality only. So let's assume this is the fx, and so minimize fx subject to g1 equal to 0 and g2 equal to 0. This is the very simple optimization problem. So, and what all are the variables in X? What all variables we need to find in X? Can you guess what all variables we need to find? What all variables are unknown here? Unknown are
P,
PG1,
PG1, PG2.
PG2, and delta 2.
Delta
Right, so these three are the variables which are there in X, and you have to assume lambda 1 for the first equality equation, lambda 2 for the second equality equation, and then you can form the Lagrange function, and you can solve using first order first, and then second order, then interior point. Probably do not solve for a lot of iterations, probably you can do it for 2 or 3 iterations. Okay, you can solve for 2, or let's keep it 2. Why to complicate? Let's keep it 2. So you can solve for 2 iterations, and after the 2 iterations, for all these 3 methods, first order, second order, interior point. So do you get the idea? So this is a very simple power system problem. Details I am going to tell you later on how these equality constraints are coming. But this is nothing but just for your understanding. This is nothing but the in power flow, Newton-Raphson, you know how to form this admittance equations, admittance matrix, and these equality equations. So basically this is nothing but the mismatch equations what you see in regular power flow expressions. So this is I'm writing from there, but later on I am going to explain you how and why we are writing these equations. Right, so can you solve this using all these 3 methods? So this will be your tutorial on Wednesday, but I'm giving you a bit early so that you have enough time, and I'll anyway just re-explain this problem on Wednesday. So if you get time, you can solve it before also. If not, then you will be given 1 week of time. So probably till not this coming Wednesday, but the next Wednesday will be the last day to submit this tutorial. Okay, any queries? So I wish to stop here because it's Saturday. So I hope you can take some relaxed time. So any more queries here? So we'll be doing probably one more lecture for optimization basics, and then we'll come back to the power system problems. Okay, so if no